Welcome to first lecture of module 4 of this course called Game Theory and Economics. So, we are starting with a new topic in this present lecture. This topic is called mixed strategy Nash equilibrium. Now, to understand what is mixed strategy Nash equilibrium, let us try to recall what was the basic idea of Nash equilibrium, the idea that we have developed and discussed so far. The idea was that there are a set of players, and these players are taking actions, and a Nash equilibrium is a situation where a player's action is optimal given the actions taken by other players. Now, when I am talking about one player is taking an action which is optimal, it is not the case that this person is taking action once in a lifetime and that is the end of it. Because if that is the case, if the game were played just once, then a player has no way to understand what are the actions that are going to be taken by other players, because if you remember, the game is a simultaneous move game. So, in the game the actions are taken simultaneously, and if the actions are being taken simultaneously a player cannot know beforehand whether a particular action of his is optimal or not optimal. So, to justify the fact that a player knows that his action or her action is optimal, the way we visualize is in the following sense, that this game is being played over and over. So, the game is played over and over. But suppose I am talking about player 1, then it is not the case that the person who is playing in player 1's position, his identity remains the same. Rather, behind player 1 there is a set of players. And all these players in this set of players have the same kind of preference and have the same kind of set of actions. So, each of them can qualify to be player 1, and similarly there is player 2, and behind him also there is a set of players. And what happens is that in each play of the game, one person gets selected, and here also one person is getting selected, and these two people are playing the game, and this selection is made randomly. And so, this game is being played many times. So, whenever there is the turn of any particular player to be in the position of player 1, this player has known what has been the history of the game before that. So, he knows that the player who has been in player 2's position has been playing a certain action, and the person who has been in player 1's position has been playing a particular action, and these actions are stable. Now, stable in the sense that they are remaining the same, kind of steady state kind of actions. Now, two actions, a pair of actions can be steady state, they can remain the same only if they are optimal to each other. Otherwise, if A is not optimal with respect to B, in the next play of the game, the player who is responsible for A's action will change his action, because that is not optimal given that the other player is playing B. So, that is why we say that Nash equilibrium is a stable steady state situation, that given the same pair of action is being played over and over again. So, suppose this is the Nash equilibrium, this is the pair of action which has been played before, and since this has been played before, whenever player 1 comes to play this action, or the player who is in player 1's position comes to play this action, he knows that player 2 is going to play A2 star, and since he knows that A2 star is going to be played, his optimal is A1 star. So, he continues to play A1 star, and the same logic holds for player 2 also, or whoever the player is in player 2's position also. So, that is why we call that Nash equilibrium is a stable steady state outcome. Now, this was the case so far. In mixed strategy Nash equilibrium, what we shall do is that we are going to change the story a little bit and make it a more generalized case. In generalized case, in the sense that here in mixed strategy Nash equilibrium, for any particular player, it is not the case that his action, particular action remains the same, but the pattern of actions, that remains the same. What is meant by pattern of actions? Suppose set of actions of player 1. Suppose this was A1, A2, AM suppose, and in Nash equilibrium what he has been doing, suppose he was taking this particular action which is AK star. So, AK star is a part of the Nash equilibrium profile. Now, AK star is going to be played again and again, the same action is being repeated by player 1. Now, instead of that, can we generalize it and say that it is not the case that AK star is going to be played by player 1 again and again, but what he is going to do is that his probability distribution over the action set, that is going to be constant, that is going to remain constant. It is not that the action is remaining constant, but the chances that the actions have of being played, that remains constant. So, it may happen that player 1 has this action set, A1 and A2, these are the two actions. It is not that A1 is going to be played and it is not that A1 is going to be played, but suppose A1 is going to be played with probability 1 by 3 and A2 is going to be played with probability 2 by 3, and these probabilities are going to remain constant. Now, and if they remain constant for each player, whatever the probabilities are for each player, then we call that to be a Nash equilibrium. So, it is a generalized concept, and it is generalized in the sense that I can have the probability to be 1 and 0 also. So, in that case I get back the original concept of equilibrium, the concept of equilibrium that we have been discussing so far, where one action is going to be played again and again. So, the concept of equilibrium that we have discussed so far is a special case of this generalized idea of Nash equilibrium, where the pattern of actions, the probabilities that the actions have in a particular play of the game to be played, those probabilities remain the same. So, that is the general case, and the fact that a particular action is going to be played with probability 1, that is a special case of that generalized case. So, this is the idea of mixed strategy Nash equilibrium. What we are going to do now is that this idea of Nash equilibrium or mixed strategy Nash equilibrium, can be interpreted in this way that I have just said, that a particular player attaches suppose probability 1/3 to his first action and 2/3 to the second action. He has only these two actions. This can also be interpreted in the following way, that this population of player 1 out of it one-third of the population So, this is an alternative interpretation of this mixed strategy Nash equilibrium. Remember, I have not rigorously defined what is a mixed strategy Nash equilibrium so far. I am just motivating the idea. So, this is the alternative idea of mixed strategy Nash equilibrium. If you remember, player 1, the identity of player 1 does not remain constant. The person who is being played, who is playing the game in place of player 1, he is selected randomly from a population. So, instead of saying that this player who is playing the game in place of player 1 is playing A1 with 1/3 and A2 with 2/3, we can also say that of the total population behind player 1, 1/3 of that population is playing A1 with certainty and 2/3 of the population is playing A2 with certainty. In this case also, since the players are being picked up randomly from the population, the probability that A1 will be played remains at 1/3 and the probability that A2 is going to be played is at 2/3. So, there are two ways to look at the fact that players are not taking any action for certainty, but is what is known as randomizing. So, this is called randomization. Instead of playing any action for certainty, a player can be allowed to attach a probability less than 1 to a particular action. So, this is what is the basic starting point of mixed strategy Nash equilibrium. We shall start with one example of mixed strategy Nash equilibrium to motivate the idea further. So, this is the familiar matching pennies game. And if you recall, the game did not have any Nash equilibrium in the way we defined Nash equilibrium in the previous sections. Incidentally, the way we define Nash equilibrium in the previous section in terms of taking an action for certain is called pure strategy Nash equilibrium. So, this matching pennies game has no Nash equilibrium in pure strategy. What we are going to show is that if we consider mixed strategy, if we consider the fact that people can randomize then this game has a Nash equilibrium at player 1 will play H with probability half, T with probability half, player 2 will play T with probability half. So, that is what we are going to show, that if these are the probabilities that player 1 and player 2 attached to actions H and T, they have two actions, then this game has a Nash equilibrium at these probabilities. Now, and we are further going to show that this is unique. That is, this is the only Nash equilibrium. This is the only mixed strategy Nash equilibrium. There is no other mixed strategy Nash equilibrium in this game. Now, to prove the first part, that this is a Nash equilibrium, what we need to do is that, given that, for example, player 2 is playing H with half and T with half, we are going to show that player 1's playing H with probability half and playing T with probability half is optimal. And similarly, given player 1 is playing H and T with half, we are going to show that player 2's choice of probabilities, that is half and half, is optimal. If we can show that, then we have shown that this is a Nash equilibrium. So, let So, let instead of half and half, let us suppose that player 1 plays H and T with probability P and 1 minus P, and 2 plays these actions with probabilities half and half. Now, if this is the case, then what we are essentially saying is the following. He is playing these actions with probability half and half, and he is playing with these probabilities. Now, in this game, there are basically two sorts of outcomes, in the sense that what happens at the end of the day, either player 1 gets 1 rupee or player 1 loses 1 rupee. Now, if I call that this event of player 1 getting 1 rupee as that event which player 1 likes, then what is the probability that player 1 gets 1 rupee? So, probability that 1 gets 1 rupee, this can happen under two circumstances. If the result is HH, that both the players are showing heads to each other, or if the result is TT, both the players are showing tails to each other. So, and these two events, that HH and TT are mutually exclusive. If one happens, the other cannot happen. So, I can write it as HH plus TT. And what is the probability that HH has happened? Which means that player 1 has chosen H, player 2 has also chosen H. Now, these two probabilities, that the probability that player 1 chooses H is P, and the fact that player 2 has chosen H, which is half, these are independent events. Now, if these are independent events, then the probability that H and H has happened is equal to probability that player 1 has chosen H multiplied by the probability that 2 has also chosen H. So, this is P multiplied by 2 plus 1 minus P multiplied by half, and this is simply half. So, the probability that player 1 gets 1 rupee is half, and what is the probability that player 1 loses 1 rupee under two circumstances: if the result is HT, or if the result is this should be T. If the result is HT, or if the result is TH, this or this. And again, like the logic before, what is the probability that HT is occurring? It is given by P multiplied by half, and this probability TH is 1 minus P multiplied by half. So, we have got half. Now, the interesting thing to notice here is that irrespective of P, the probability that player 1 gets 1 rupee or loses 1 rupee remains at half. It is independent of P. So, whatever P player 1 fixes, whatever P, which means that probability of showing H player 1 attaches, the probability that he gets 1 rupee or loses 1 rupee, that remains constant at half, which means that any P is optimal. So, optimal in the sense that player 1 always likes to get 1 rupee. So, he would always like to have as much probability attached to this event as possible, but here any P is optimal, because this is independent, this half is independent of P, and if any P is optimal, then P is equal to half is also optimal. Right. Now, this was from the point of view of player 1. The similar logic can be also applied for player 2. Here we are going to look at the game from player 2's point of view. So, to do that, let us suppose that player 1 attaches half and half probabilities to H and T, and player 2 attaches Q and 1 minus Q to H and T. Now, in this case, probability that 2 gets 1 rupee, 2 gets 1 rupee in this circumstance and this circumstance, and what is the probability of that? Half Q plus half 1 minus Q, which is half, and similarly one can show that P loses 1 rupee, that probability is also half. I am not going to show this last one, but it is easy to show that. Which means that given that player 1 is playing H and T with half and half, the player 2's probability of getting 1 rupee or losing 1 rupee remains fixed at half, which means that player 2 can attach any probability to H and T, and any such probability will be optimal. So, any Q is optimal. So, Q is equal to half is also optimal. So, what we have derived is the following: given Q is equal to half, P is equal to half is optimal, and given P is equal to half, Q is equal to half is also optimal, and therefore, P is equal to half, Q is equal to half is Nash equilibrium. So, that is the proof that in mixed strategy, if we consider mixed strategy, if we consider that people can randomize, then in matching pennies game, there is a Nash equilibrium where P is equal to half, that is probability of 1's playing H is equal to half and 2's playing H is also equal to half. This combination of probabilities is a Nash equilibrium. Now, the next part is uniqueness, that this is the only Nash equilibrium in this matching pennies game. Now, to prove that this is the only equilibrium, what we need to assume, which is a very simple assumption, is that any player will like to maximize the probability of his getting some higher payoff than not getting some higher payoff. For example, if someone is getting A and B under two circumstances, and suppose these are the probabilities, then if P is greater than Q, then this is this probability distribution 1 So, given that A is preferred to B, the probability distribution where A is getting higher probability, that probability distribution will be preferred by the player. By the way, this probability distribution of occurrence of these events are known as lotteries. So, these are lotteries. It is a technical name. A name that we are going to use more, very often. Now, this is a kind of innocuous assumption, but we are going to stick to this assumption, and for proving uniqueness this assumption is required. Now, let us suppose in general case that the probabilities attached to these actions by these two players are P 1 minus P, Q and 1 minus Q. So, this is the general case. Now, like before, what is the probability that player 1 gets 1 rupee? Now, this again occurs if HH occurs or TT occurs, and the probability of those two occurring are PQ plus 1 minus P 1 minus Q. And if I simplify this, this is what I get, 1 minus Q, 2 PQ and minus P. So, this is the probability that player 1 gets 1 rupee. It is 1 minus Q plus P multiplied by 2Q minus 1. And what is the probability that one loses 1 rupee? So, this will be given by this happens or if this happens, and the probabilities are P multiplied by 1 minus Q and Q multiplied by 1 minus P. Now, remember that what player 1 is trying to do. Player 1, we are going to say that player 1 will like to maximize this probability. The fact that player 1 is getting 1 rupee, that is going to be maximized. The probability of that event is going to be maximized. Now, in this case, so let us recall this. If Q is suppose not equal to half, because I know if Q is equal to half, then P is also equal to half, that is a Nash equilibrium. But suppose Q is suppose less than half. If Q is less than half, then this value becomes negative, right? And if this is negative, then what should player 1 do? Player 1 should attach P is equal to 0, then 1 will attach probability P is equal to 0, because this is negative, this probability is sought to be maximized, and so P will be set to equal to 0, which means T will be played with certainty by 1. Now, remember, if T is being played with certainty by player 1, so this is being played with certainty by player 1, what should player 2 do? Then player 2 will play H with certainty. So, in that case Q is becoming equal to 1. So, we started with Q less than half. We have seen that if Q is less than half, then P is equal to 0, and if P is equal to 0, then Q becomes equal to 1, it no longer remains less than half. So, we do not have any Nash equilibrium if Q is less than half, and similarly if so, no Nash equilibrium. Similarly, if we take Q is greater than half, then what will happen is that this is positive, then P becomes equal to 1, and if P is equal to 1, then what happens? So, player 1 is playing this with certainty. In that case, player 2 will play T with certainty, which means that Q is going to be equal to 0. So, once again we have the familiar thing that we started with Q greater than half. The optimal response from 1 is that setting P is equal to 1, and if P is equal to 1, then Q becomes equal to 0. So, we do not have any Nash equilibrium here, which means that if we take any Q which is not equal to half, we do not have any Nash equilibrium. Similarly, we can show that player 2's probability of gaining one can show that there is no Nash equilibrium if P is not equal to half. So, what we have shown is that no Nash equilibrium So, the only Nash equilibrium there is in this game is where P is equal to half and Q is equal to half. The fact that this is a Nash equilibrium we have just shown before, and now we show that this is a unique Nash equilibrium, there is no other Nash equilibrium. So, that is that. Now, to recapitulate what we have done, let us recapitulate and we go to the next step, is that here we are considering the fact that players have different actions and they randomize, they do not play any action with certainty, and if they do not play actions with certainty, then the probability that any action profile is going to be played remains uncertain. It may have a probability less than 1, greater than 0. For example, let us take the following game. So, this is A1, A2, B1, B2, and here let us suppose player 2 is playing this action with certainty. So, this is going to be played. Now, had player 1 played A1 with certainty, then we know that the outcome would have been, let us suppose, A1 B1, and the payoff from this is C1. Now, the deviation that player 1 can take is like he can go to A2 and then the outcome becomes A2 B1 and the payoff becomes C2. So, player 1 when he is deviating, he needs to consider between C1 and C2. This is not a very difficult task. So, that was the case of pure strategy. But when we have these two actions by player 1, he has only two actions to choose from, and he is considering deviation from this action A1, then there can be infinite number of deviations, because he can randomize. For example, so these are the two actions. Suppose the probabilities are P1, let us not write P1, give me a, let us call this 1 by 10 and this is 9 by 10, it can be half half. So, there are infinite number of such possibilities. If there are infinite number of such possibilities, then player 1 has to compare all these possibilities, the payoffs from all these possibilities with what he is getting at present, which is this C1. So, the task becomes a little difficult. It becomes even more difficult if there are, suppose, 3 actions. So, suppose I have another action. Now, previously there were just 2 actions to choose from. Now, I have another action A3, and previously it was easy to see if I do not have A3, suppose, if C1 is more than C2, then which one will be more preferred? All these lotteries, suppose this is P1, this is P2, etc., etc. That lottery will be most preferred by player 1 where the value attached to this A1 is the highest, because from A1 he is getting C1 which is higher than C2 which he is getting from A2. So, whenever the probability of occurring of A1 B1 is there, that probability will be sought to be maximized by player 1 if there are only 2 actions A1 and A2. But if there are 3 actions, the story becomes more complicated. Then it is not that simple rule of thumb that you attach higher probability, in which in the case where the payoff is higher. And the story becomes even more complicated if player 2 is not playing this with certainty, but suppose he is also randomizing. In that case also, this maximization of probability attached to A1 is not going to be optimal, because I do not know whether that action is going to be played with certainty, that outcome will happen with certainty. So, if I have more than 2 actions or more than 2 outcomes, then the lottery or the preference over lotteries becomes a little difficult to figure out. So, it is like this. So, this is the preference of a player. A is preferred over B, and our the model that we had so far, that if there are 2 outcomes, then if P is greater than Q, and these are the 2 lotteries, lottery 1 is preferred over lottery 2. If I have 3 outcomes and I know the preference ordering of the outcomes, suppose I have 3 outcomes A, B, C, and suppose to have a concrete idea, suppose I am comparing between 2 lotteries. This is one lottery and this is another lottery. Now, can we say for certain whether 1 will be preferred to 2 or 2 will be preferred to 1? We cannot know if we do not have any further information regarding players' preferences. Remember here what is the previous rule of thumb was that if you prefer A, you prefer that lottery where A's probability was highest. Here in 2, A's probability is 1/3, which is greater than 0. 0 is occurring here. But even then it may happen that a player chooses 1/2. It may happen because the player may like to have a situation where this middle one is occurring with certainty, because in the last one there is a high chance that the last C, which is the least preferred, that outcome occurs with quite high probability, 2/3. So, it is very probable that any player will like to have A over B. B lottery will not be preferred, A will be preferred, where B is guaranteed, where A and C are not probable. So, if I have 3 outcomes or more than 3 outcomes, unlike in case of 2 outcomes, I cannot know beforehand which lottery will be preferred by a particular player. And in this case, the lotteries are going to be important. For example, suppose I am talking about player 1's payoff from a game, which is a very simple game. Suppose these are the why the lotteries are important is the reason is the following. If player 2 plays this action with Q and this action with 1 minus Q, player 1 is playing this action with P and this action with 1 minus P, then what is the payoff of player 1? It is given by PQ multiplied by C1 plus P1 minus Q multiplied by C2, 1 minus PQ multiplied by C3, 1 minus P1 minus Q multiplied by C4. So, these factors PQ, P1 minus Q, 1 minus PQ, 1 minus P1 minus Q, these are the probabilities attached to these 4 outcomes, and these are then the lotteries attached to the outcomes. So, these are the probabilities PQ, so they are similar to this this P's here or these P's here. So, if I have more than 2 outcomes, then how does one figure out which lottery one prefers over other lotteries? For this one assumption that we are going to take is that the preference of the players are so the preference of the players are von Neumann Morgenstern, which means that there is a particular kind of preference which is called von Neumann Morgenstern preference. The players preference obey that property, the property of von Neumann Morgenstern preference. And what does it mean? It means that if A, B, C are the outcomes and P1, P2, P3 are the probabilities attached to them, then utility or the payoff from A, B, C with the probabilities attached P1, P2, P3 is the expected value of the payoff functions from the certain events. So, this is going to be P1 this and this small u's, these are the payoff functions defined over deterministic outcomes and these are also called Bernoulli functions. Bernoulli payoff function or Bernoulli utility function. So, if the preference of the player satisfy von Neumann Morgenstern preference, then it is possible to rank the different lotteries that people face. So, if people have a particular player is facing two lotteries, suppose one is P1, P2, P3 and suppose the another lottery is there where the probabilities are different Q1, Q2, Q3. Then I apply this formula over this lottery also and I get this. And then it is easy to compare because this is a number, this is again a number. If this number is higher than this number, then this lottery is preferred to this lottery and vice versa. If this number is higher than this number, then this lottery is preferred to this lottery, and if these two numbers are equal, then the player is indifferent between these two lotteries. So, this von Neumann Morgenstern preference pattern gives us a clue how to compare the preference of players over lotteries. Now, it is by no means a sacrosanct kind of assumption that people's preferences are going to satisfy von Neumann Morgenstern preference. It may very well happen that they do not satisfy von Neumann Morgenstern assumption, the characterization of preference that these two economists, von Neumann was a computer scientist first, and then he worked with Morgenstern, an American economist, and they proposed this kind of preference pattern to deal with cases of uncertainty, because we have lotteries here. So, uncertainty where the things are not very certain, there are probabilities attached to an event, then we have to use some criteria of how to judge people's preference, and this is a clue. This is a clue which has been proposed by von Neumann and Morgenstern, and this is also known as expected utility theory. Okay, now before we finish this lecture, let me take you through what we have been discussing in this lecture. We have started the discussion about mixed strategy Nash equilibrium First we discussed what it deals with, the fact that people can randomize over actions, that is sought to be captured by this mixed strategy Nash equilibrium, unlike the case of pure strategy Nash equilibrium. Then we discussed about an example in case of matching pennies. In case of matching pennies, we have seen that there is a single mixed strategy Nash equilibrium where the probabilities are half and half. And then we started the discussion about how to rank lotteries, which lottery will be preferred to other lotteries if we have more than 2 outcomes. And talking about that, we have introduced the idea of von Neumann Morgenstern preference. We shall continue from this in the next lecture. Thank you. What is meant by stochastic steady state or mixed strategy Nash equilibrium? So, stochastic steady state. This is the case where players can play actions with probability less than 1. So, they randomize, or let us say they can randomize, they may not randomize their actions now. Here if the players play the actions with the same probabilities and that is optimal, okay, same probabilities in each period and that is optimal, then we have stochastic steady state. So, here what is not there is that it is not required that the players play the same action every time. What is required is that they play the actions with the same probabilities each time, and that is called a stochastic steady state. Stochastic means related with probability, since the probabilities are remaining steady. So, we are calling it a stochastic steady state, and such stochastic steady state if it prevails will be called a mixed strategy Nash equilibrium. Show that the BOS game has a mixed strategy Nash equilibrium at P 2/3, Q 1/3. Let us remember the BOS game. So, we have to prove that 1 is assigning 2/3, 1/3 and B is player 2 is assigning 1/3, 2/3 to their actions B and O, and that is a mixed strategy Nash equilibrium. Yes. How to prove? Now, given Q is the probability with which player 2 plays B, Q is 1/3. Expected payoff of 1 from B is given by simply 2 divided by 3, and expected payoff of 1 from O is similarly given by 2/3. So, for player 1, it does not matter what probability he attaches to B or O. Any division between B and O will be optimal. Hence, 2/3 1/3 is also optimal. Okay. So, this is one part. Secondly, given P is equal to 2/3, expected payoff of 2 from B is how much? It is given by 2/3, and expected payoff of 2 from O is again 2/3. So, they are equal. So, any division is of probabilities between B and O is optimal. Therefore, 1/3 2/3 is optimal for 2. So, therefore, this is a Nash equilibrium. Thank you.